In Chapter 4, we start the conversation of probability, and in this lecture video, we'll be going over some of the basics. We first want to be able to calculate the probability of an event, and in order to do that, we need to go over a few definitions. An event is any collection of results or outcomes of a procedure. An example of a procedure might be flipping two coins, and an event in this case might be having the coins land with one on heads and one on tails. A simple event is an outcome or event that cannot be broken down any further. So with our example of flipping two coins, we had the event of having one coin land on heads and one coin land on tails. The simple event in that case would be that the first coin landed on heads and the second coin landed on tails, or the first coin landed on tails and the second coin landed on heads. Can you see how these simple events are broken down as far as they can be in comparison to the event of simply one heads and one tails? A sample space is the collection of all possible simple events for a given procedure. So again, with this example of flipping two coins, our sample space would be the collection of all simple events. We could have both coins land on heads, the first on heads and the second on tails, the first on tails and the second on heads, or both on tails. So our sample space has four simple events. To look at this through a slightly different lens, let's use a tree diagram and create the sample space for the procedure of flipping three coins instead of two. When we flip the first coin, there are two options. That first coin could land on heads or it could land on tails. If the first coin lands on heads, then there's two choices for the second coin. The second coin could land on heads, or the second coin could land on tails. Similarly, if the first coin lands on tails, the second coin could land on heads or tails. And that brings us to the third coin. If the first coin lands on heads and the second coin lands on heads, we have the same two options for the third coin: heads or tails. If the first coin lands on heads and the second on tails, the third coin could be heads or tails. And the same is true for the last branches of the tree. This is what we call a tree diagram, and it helps us create sample spaces. It helps us see all the individual possible simple events. Each option listed in the last column represents a simple event. The first one represents the simple event of all three coins landing on heads. The second represents the simple event of the first two coins landing on heads and the third coin landing on tails. The third one represents the simple event of the first coin landing on heads, the second coin landing on tails, and the third coin landing on heads. And the fourth represents the simple event of the first coin landing on heads, second on tails, and third on tails. And we can list out the last four simple events in the same way. Now we have the sample space for the procedure of flipping three coins. Now let's talk about how we calculate the probability of an event A. The way we notate this is a capital P with the event A inside of parentheses, and we read that as the probability of event A. We can calculate this probability by taking the number of times event A occurred and divide that by the number of times the procedure was repeated. Depending on the situation, a slightly different phrasing can be helpful. We can consider this to be the number of ways that A can occur and divide that by the total number of possibilities, or all different options for simple events. Let's use this to find the probability that in exactly 3 births, a couple will have exactly one child assigned female. In order to calculate this probability, we first need the sample space. We need to know all possible options, all possible simple events that could occur. With 3 births, the sample space looks something like this. They could be all assigned male. There could be 2 male and 1 female in 3 different ways. There could be 1 male and 2 females in 3 different ways. Or all 3 children could be assigned female. Now that we have our sample space, we can calculate the probability that one child will be assigned female. That's the same as saying that we want the probability of having 2 children assigned male and 1 assigned female. And this is equal to the number of ways that this can occur, 3, divided by the total number of possibilities, 8. And in decimal form, we find that the probability is 0.375. Sometimes we'll be given the results of a procedure in a table. Let's take a look at this example with the results from experiments with polygraph instruments. A polygraph instrument attempts to determine if a person is telling the truth or telling a lie. In this graph, we can see the number of people that lied or did not lie and the corresponding polygraph reading. For example, we can see that 15 people did not lie, but the polygraph instrument said that they did. And 9 people did lie and got away with it. Our job in this example is to find the probability of getting a negative result. And we can calculate that by finding the total number of people that got a negative result, that is, how many times this occurred, divided by the total number of times that the procedure was repeated. And in this case, that would be the total number of people that participated in the experiment. First, let's figure out how many people got a negative result. That is, the polygraph test said that they did not lie. Looking at this row here, we can see that 41 people got a negative result. We need to include those that lied and did not lie. So 41 is our numerator. And by adding up all 4 boxes, we can see that a total number of 98 people participated in this experiment. So our total, or denominator, is 98. And calculating 41 over 98, we find that the probability of obtaining a negative result is 0.42. Notice that this probability calculation does not take into account whether or not the person was telling the truth or telling a lie. We simply calculated the probability of a randomly selected person getting a negative result. If a procedure is only repeated a few times, the results could be just about anything. However, as a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability, or the theoretical probability. For example, if you flipped a coin just 3 times, no one would be too surprised if the coin landed on heads 2 times and tails 1 time. That is, the coin landed on heads 2/3 of the time. However, if you repeated the procedure of flipping a coin 1,000 times and 700 times it landed on heads, you might become a little suspicious of that coin. Repeating the procedure so many times, you would expect that the probability would start to get closer to 50-50, the actual probability. That brings us to some other important characteristics of probability. If an event is impossible, then the probability of that event happening is 0. If an event is certain to occur, then the probability of that event happening is 1. For any event A, the probability of that event happening is between 0 and 1 inclusive. In other words, the probability of an event A is greater than or equal to 0 and less than or equal to 1. The complement of an event A, which we write A bar, consists of all outcomes in which A does not occur. If the probability of an event happening is very, very small, then it is considered unusual if that event does occur. Let's take a look at this example. If the probability of a car being involved in a car crash is 0.048, what is the probability of not getting into a car crash? You can probably figure out this answer intuitively, but let's use some proper notation to practice what we just wrote down. We are given that the probability of getting into a car crash is 0.048. We are asked for the probability of not getting into a car crash, which is the opposite of being in a car crash. So it's all of the other options. In other words, we expect the probability of getting into a car crash and not getting into a car crash to add up to 1. So to calculate not getting into a car crash, we have 1 minus 0.048. or 0.952. That's what we mean by the complement. No car crash is the complement of car crash. So when we're calculating this probability, we are really calculating the probability of the complement of a car crash, the opposite of a car crash. That concludes this lecture video on some of the basics of probability.